Hey everybody, we got to do, as I said, we're going to talk today about, as you saw in the first two videos, we're going to talk about center of mass. They were pretty cool videos, I thought. I liked them, and that's why I assigned them, because I really thought that they illustrated the point relatively well. And the second video, I don't think they ever really made clear what was so cool about it or weird. What they did is they had the person, they were holding on to the chair. Again, my terrific drawing skills come in handy. And oops, let me undo that. Undo that. There we go. Okay, so they had a chair like this, and they had their head against the wall. Okay, supposedly it's their arms, and they're holding on to the chair. And while they're doing that, they try to lift their head backwards like this, and they fall, and the boys fall over, or they just can't do it. The girls don't. Get a folding chair and try this at home. It really works. And the reason is because boys' center of mass is lower in their body. So when they try to put a force up top to move their head, they can't. They fall over. Girls' center of mass is higher. So it turns out that the holding of the chair doesn't have as big an effect. That's the idea that they were trying to show in that video. And then it has to do with the center of mass. And again, you know, if you think about it, they showed a good example, I think Dr. Carlson did, where he had a rod like this connected to some small weight like that. And they didn't balance in the center, they balanced here. I want to point out that the center of mass is absolutely not the point where half the mass is on one side and half is on the other. It absolutely is not that, unless the object is uniform. In other words, if we had instead just a uniform plank, yeah, that's uniform, right? Okay. But the idea is that in this case, the center of mass would be here. In this case, it wouldn't be here. It actually ended up being closer to there. It has to do with a concept we haven't talked a lot about, which is torque. But we don't have to know much about that to figure out what the center of mass is. Center of mass is just a weighted average. The position of the center of mass is just a weighted average, where things that have greater masses have positions of greater importance. To take a weighted average, we have to assign where the zero position is. We can actually decide it anywhere we feel like. It's an arbitrary decision, because we'll get an answer in terms of an answer that depends on our input. As long as we're consistent, it's all good. So what we're going to do is we're going to take the actual equation is x, the center of mass. It doesn't have to be horizontal, it can be in any direction. It's going to be the mass of the first thing times its position plus the mass of the second thing times its position plus the mass of the third thing times its position plus however many masses you have. I'm sorry, n masses. I mean, there's no specific number. And it's going to be divided by the total mass. So then we each thing is going to get the right weighting, and then we'll divide by the total and we'll get it to come out. Okay. So let's try an example. Let's say we have the object that they showed in the video, that this is connected by a rod of very small mass, 1 and 2. The mass of 1 is going to be, let's say, 10 kilograms. The mass of 2 is going to be 0.5 kilograms. And the mass of the rod is very close to 0. So, what's the center of mass? Well, from Dr. Carlson's video, you saw that it's going to be close to here. Let's figure out what it is using our new equation. We also need to know that the distance between these centers is 2 meters. So, we say center mass equals, and we got to call, first we got to decide where 0 position is. Let's assign it here. Now your first thought might be, well, you don't want to assign it there because that's where the biggest mass is. We'll see how that works out. We're going to have 10 kilograms times 0 plus 0.5 kilograms times 1 meter over 10 plus 0.5 kilograms. Nothing terrible. And you can see how the math's going to turn out. 0 plus 1/2 times 1, or 2 meters, I'm sorry. That's going to lead to 1 kilogram meter over 10 plus 0.5, 10.5 kilograms. Divide out. We get 1 about 1/10, a little less, so maybe 0.09 meters. Okay, about. That's actually, if you look, that's pretty close to what we said. It'd be real close to this edge, maybe even closer than what we showed. So that's good. But what about if the connecting piece has mass? Well, what we can do, if that's the case, is we can say all connecting pieces are all of uniform mass. They can be treated as the point, or as a point particle at the center of the piece. So for example, if this is a uniform piece and it is, I don't know, 6 kilograms, well, we can treat it the same as a 6 kilogram mass that is in the center. That's 3 kilograms from the edge. Okay. These are going to be equivalent for our calculations. And if you think about it, it makes sense, because you'd have something from here, 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 something from here. They'd add up and average to something in the center. Okay. So let's try the same problem, but give it some mass in the piece that connects. Now that should, since there's more mass toward the center, it should shift everything slightly. So we're going to keep all the same lengths. We're going to have the same number of kilograms for this piece. We're going to have the same number of kilograms for this piece. But we're going to assign this a mass of 1 kilogram. Not a lot, but enough to make a shift. So let's find the center of mass using our calculation. It's going to be, again, we're going to call this 0. So it's going to be 10 kilograms times 0 meters, plus we've got the rod in the center. We're going to have to consider that. That's 1 kilogram, and we're going to call it 1 meter because it's in the center, plus 0.5 kilograms times 2 meters. Remember, it's still at the other edge. All divided by 10 plus 1 plus 0.5 kilograms. Oh, 0, 1, 1. So we've got 2 kilogram meters over 11.5 kilograms. Well, that is significantly bigger than the other one. Not quite double, but pretty close. I would say that it hits probably about 0.18 meters. Again, not that far from the edge, but a lot farther than before. You can check it out through your calculator. Okay. Another way to write this equation, I've seen it written as like this: the sum of m n x n from n equals 1 to, I don't know, the number of objects, and the sum of masses. I should be, that's how you're supposed to write it. You're supposed to say I equals 1 to n. So this one should be I equals 1 to n. It should be mi xi. I'll write it again. 1, sorry, I forget these little math things. Over. This is another way to write it. Sum I equals 1. Cool. That should give you enough to do the problems.